So I'm here to talk about JavaScript robotics and why it might not be a bad idea. Real quick, who am I? I'm the co-organizer of a JavaScript user group in Ann Arbor called Southeast Michigan JavaScript. I'm also a team player at Care Evolution. It's a healthcare company in Ann Arbor. We do things a little bit differently than most healthcare companies, or most companies at all. We're approaching 100 people, but completely flat organization, no managers, no time tracking, no vacation tracking. You get to make your own titles, so I'm team player. It's kind of a cool place to work. It's not for everyone, but we are hiring and you can work remotely. So we can talk about it at the bar or something like that afterwards. I'm also a team player on Johnny 5. It's the framework I'm going to talk about a bit today, as well as Robotnik, another thing I'm going to show. Neither of them are my creations. I just help on them because I'm excited about what's happening in this space. I'm also a hacker, dad, and husband, so I like to hack domestic things. I like to hack my cooking and hack my kids and things like that. Just part of who I am. So I got the idea for this talk because one of the things I also like to do is organize robotics learning events, specifically NodeBots, which is JavaScript plus hardware. And I was doing my very first one. It was a hackathon at my company. Every 8 weeks we do this hackathon where everybody just kind of tries something new and you know, maybe it's related to work, maybe it's not. And so I organized a BattleBots. It was 16 people were doing it. We got a whole bunch of kits, Arduinos. The kits looked a lot like this, and we'll talk about that a little bit later. Everybody's having a lot of fun. 16 people, 8 robots, and I'm helping somebody debug. And off to the left, somebody who's not participating is like, hey Brian, using JavaScript for hardware, it just sounds like a really bad idea. I was just, I didn't know where he was coming from. It was like, you're not involved with this. You have no skin in this game. We're having fun. What's going on? And he was like, using dynamic languages for hardware just sounds dangerous. Anybody worked with hardware in the past? Usually it's in C, C++. Usually you can do it in other things. Have you ever fried your hardware in C and C++? Yeah, it's not the language. It's hardware. It's part of what happens when you're in hardware. I have a background in embedded systems. I don't use it in my day job anymore, but I've fried plenty of hardware. I even bricked an Abrams tank once. Not kidding. We got it back, but so not technically bricked, but it's a couple days without booting. I corrupted the bootloader. Anyways, but you know, for me, I've paid my dues. I've done my C and C++. I could do it again now if I wanted to. I choose not to. I don't want to deal with cross-compiling and make files and the macros in C and getting the right libraries and esoteric errors and all the stuff that comes along with it when I'm hacking hardware, because really I just want to have fun. For me and for many people who are going to be doing robotics at home or whatever, they don't want to. They just want to play. I actually go on Friday nights. I go to the bar with my little robots and my laptop, and I hack away. And I just don't want to deal with C compilers. And it turns out JavaScript actually does have some good parts to it. It's got bad parts too, there's no question, but one of the biggest things that JavaScript has going for it is it's accessible. And if you were to take the set of people with awesome ideas and the set of people who know JavaScript, because quite frankly, all you need is a text editor and an operating system to try out JavaScript. You don't have to download a C compiler or anything like that. It's a pretty big set. It's just a smaller set in C and C++. Again, it's not that you can't do it, but by bringing things over to JavaScript, you're just making things more accessible. And because JavaScript is interpreted, debugging is a lot easier. And there are a lot more, it's just easy. It's easy to just write some script and get going. And it's also good at asynchronous and event-based programming. C and C++ can do it. You can pass around function pointers, sure. But the functional nature of JavaScript makes it very, very easy to do async programming, especially if you're in Node.js, which is asynchronous by nature. Pretty much everything you do is non-blocking, except for a few legacy file read calls or whatever. And so it ends up working really well with hardware, which tends to be asynchronous. It's very, very rare that you can say, go read a pin and get the result. I guess you can do it with pins, but if you're talking on an I2C bus or something like that, you're not going to say, go read and have it immediately. You're going to say read, and then the data's going to go out, and then it's going to come back, and then you're going to get your data. And so you can then just say read, and then when you're done, here's your function. JavaScript is also really good for writing abstractions. Has anybody ever heard of jQuery? A few of you, right? What is it that jQuery does? If you were to sum up what jQuery does, what does it do?
It abstracts the DOM.
It abstracts the DOM. Exactly. It takes all the different DOMs that have these differences in them and makes them have the same API everywhere. And JavaScript's just, by nature, its dynamic nature, it's good at that. And so there's this library that I'm going to talk about a bit today. It's called Johnny5, and it does that. It is like jQuery for hardware, meaning you've got lots of different I/O boards. You've got Arduinos, you have BeagleBones. Somewhere around here I've got my, oh, here it is. This thing's called an imp. We'll talk about this a little bit later. You got all these different boards, and Johnny5 says, well, okay, they all have the same interface. And then you've got all these different components. These are just a handful of accelerometers you can go on Amazon or SparkFun and buy. And if you do this in C, each one of them has a different library that goes along with it with a completely different API. But in Johnny5, you get one API, and all you do is say it's this type of accelerometer, and it just works. So in other words, different hardware, same shape. And the community is going wild right now. If you look at the pull requests that are happening on this project alone, you'll find that there's a whole army of people writing these little tiny device drivers, essentially, for all these different pieces of hardware. So I can just go off the shelf and get an accelerometer, and it'll just work. Which actually makes it really ideal for open source projects. Now you don't have to bring down the code and then say, well, I'm going to have this. You have to have this accelerometer. I just need an accelerometer and a little configuration saying where it, which pins it's sitting on, and then the software just talks to that same API. And so it all started with the Arduino. We all know what an Arduino is. This is an Arduino. I think this is an Arduino. There are different types of Arduino, but it's a very, very small microprocessor with lots of I/O, input-output pins on it. Analog, digital, a couple different buses that it communicates on. It started with Arduino, but it branched out. The BeagleBone Black. This thing, so the Arduino you can get for about 15 bucks, right? This thing, a little more expensive, 45 bucks, but it's running Linux, and it's running the Cloud9 IDE right out of the box. So you just plug it in, point your browser to it, and you've got an IDE right there, and you just start writing JavaScript in your browser, and you're controlling this thing. And so we'll get to the architecture a little bit more. This thing here is the JavaScript doesn't actually run on the board. It runs on another computer through a communication mechanism. This one here, the JavaScript runs right on the board. There's also the Raspberry Pi, supported by this platform. Intel has two different offerings called the Galileo and the Edison. Also, like the Raspberry Pi and BeagleBone, they run Linux. In fact, the Galileo runs a flavor of Windows 8, which is kind of funny, a headless version of it. And Johnny5 isn't supported on there. I couldn't even get Node to work on it. maybe there's a way to do it, but I guarantee Johnny 5 won't work. The Spark core, that's another really cool one. It has the pinout compatibility of an Arduino, but it's a much smaller profile, and it has a Wi-Fi chip built in. And so you can communicate to it. And so it uses the same model as the Arduino, where the code runs on on a computer or a Raspberry Pi or a BeagleBone or whatever, and sends commands over to the Spark core. But it does it through Wi-Fi. The electronic imp, this is one of my favorites. And we're going to have a demo with this a little bit later. The entire microprocessor and Wi-Fi chip is on this SD card. So then what you can do is you can design your hardware to take an SD card and then buy these things and just snap them right in. This is just a development board for it. It just it takes the pinouts and allows you to manage it. But talks through the cloud. It's really quite amazing. 25 bucks. Really accessible for hacking. Doesn't take much. The light blue bean is similar. It uses Bluetooth instead of Wi-Fi. The Pinocchio is designed for more mesh computing. You'd have a lot of these around and they all talk to each other. Same thing. But with all this hardware support and all these things that make it a good reason to use JavaScript, Johnny 5, Node, etc., it's really the community. You can do these things in Python too. And you can, all the things that I just said are true of Python, or name your language, your more modern language. But the community in this space is probably an order of magnitude more active than the other spaces. Don't know why, other than the fact that the Node community is also extremely active. There's just a ton of stuff happening, and the moment you are running your code in Node, you now have all the packages that are available in Node at your fingertips. It would take 4 lines of code for me to take this Arduino and put it on the web, for example. Just bring down a Connect web server, and then, then say when the data comes through, return, store it and send it down for REST requests. I mean, it's really straightforward. Just a lot going on there. So before I get into looking at the architecture and some examples and how this all works, any questions yet about what I've said? Any objections to it? Okay. So this is the layer of abstraction for the entire stack. You have your code. This is your business logic, essentially. If I have a car here, what's my business logic and my business objects? I have wheels, and my wheels go counterclockwise and clockwise. And so if I want to go forward, if you think about a car, forward, the left wheel needs to go counterclockwise, and the right wheel needs to go clockwise. Right? That's your business logic. Pretty straightforward business logic, but that's the code you want to focus on. You don't want to focus on electronics. That's because Johnny 5 takes care of that for you. Now, Johnny 5, by default, has to talk to an I/O layer. And in Arduino, it's something called Fermata. Now, Fermata is a serial standard for Arduinos to talk through the serial port, which is really the USB port. And every language you can imagine has created a host API to talk Fermata, because Fermata comes out of the box with Arduino. If you bring down the Arduino suite and go to the examples, one of them is Fermata. It's called standard Fermata. You load it on the board, and it's ready to talk over the serial port, over the USB port, this Fermata. And so you'll find all sorts of things. But most of them stop at this layer. They just say, okay, well, you can turn a pin high, you can turn a pin low, you can send something to the I2C bus, and what that means doesn't matter, it's data bus. But it's really still really low level. How to talk to the hardware is usually still up to you. And that's where Johnny 5 sits and says, well, I know how to talk to all these different components, and I'll do it for you and give you an API, so you're not talking to a pin, you're talking to a servo. So that's the software layer. Then that talks to the native API of the board. In the case, I forget what it's called on Arduino. Is it pinning? It's just, there's an API in Arduino that tells you how to turn things on and off. And that talks to the actual Arduino, which then sets pins high and low, which then talks to your components. If you were to just write Arduino code, you'd be writing at this layer. So it's just a couple of layers of abstraction above that Arduino layer. So let's talk a little bit about just controlling some servos. This right here is a platform I like to play with because it's so simple. It's an Arduino and 2 servos and a breadboard so I can wire things up. And so often I'm not even using the servos, I'm just wiring a few things up over here because it's sitting here. It's just a platform I can take with me. And I've also got a reflectance array, and I'll get into that in a moment. But let's forget about the reflectance array. This car, in the back of it, has a little caster. So really the drive is these 2 wheels. If you want to turn left, you just turn one way and turn one the other way and pivots. And so you can control it. So this demo here is going to show how to just control this car. I'm sorry, my LED popped out. How to control this car via Johnny 5. Now, let's look at the code first before we run it. This is using Node and NPM, and that's kind of beyond the scope of the talk. But the idea is here you require the Johnny 5 library. You create yourself a board. This is the board abstraction. And it takes a little while for the board to boot up. And so it takes about 3 seconds for an Arduino to boot up. And so this is the asynchronicity. I say when the board is ready, then let's configure the rules here. And I say the right wheel and left wheel are just servos on pins. And if you can see it here, there's really just 2 pins here. And we're on 7 and 11 for those pins. And it's just plugged into the board directly. And it's a continuous servo. So there are 2 different primary types of servos out there for rotational servos. One of them is the type you would use in RC airplanes, where you would say, I want to go to 45 degrees or negative 45 degrees. They're specific degrees. But there's another type of servo called a continuous servo, which just continuously rolls in either direction. And those are really useful for something like this because they're really just motors with motor controllers and transistors and H-bridges and all sorts of things that you would have to wire up yourself to work with a motor. It's just kind of built into one nice little package. And then the cool thing is, once I got these wheels, if I want it to go forward, I say clockwise and counterclockwise on those 2 wheels, and they'll go forward. And so this very, very simple example is going to have the car go forward. Then after 1 second, it's going to go backwards. And then after 2 seconds, it's going to stop. And the thing I want to really point out here is that because we have these abstractions for these servos, these are the only 2 lines that you really need to think about hardware right here. The rest is the logic of your system. You've abstracted the servo out and saying, I have wheels, not servos. I don't care that they're servos. They might be motors. They might be, I don't know what else they'd be. But it doesn't matter. It could be anything. What I really want to do is I want to say that it's going to go clockwise or counterclockwise. And so we'll just run this demo, and you'll be shocked at what it does. Right? Pretty cool. But like any system, you want your own abstractions. You don't want to put everything all in one file, and so that's when, this is the wiring for it. Really straightforward. You got power, you have ground, and you have the pin. You get more servos, you may want to isolate the power, but in the simple example like this, we're just plugging right into the board. But now we can expand this and say that there's a car class or prototype, in JavaScript. And I can say, I'm going to pass in Johnny 5, I'm going to tell you what the right pin and left pin is, and then again, you have your configuration here, there you have 2 servos, then everything else here, forward, reverse, right, left, and stop, are all just functions on a class. And so now I can control this thing using my keyboard. I just create a key map. I'm using standard in, and when I get a key press, I look to see is that key press in my key map? If it is, just call the function on the car. So this is kind of like your controller calling the class. And very similar demo expands out to let me now drive my car around. Now, of course, yeah, you've got this to deal with. Okay. Now, this wire is really kind of a pain, right? It's not hard to make this Wi-Fi or Bluetooth enabled. It doesn't demo well, especially depending on how large the group is and how large the space is, because Wi-Fi fails and people are using Bluetooth all over the place at things like this. I use the cable, but there are solutions out there for using Bluetooth and Wi-Fi to do that. Or you just upgrade to a board where the JavaScript runs directly here. Same story, it doesn't have to be tethered. But this demo is just Arduino tethered. Just one configuration. Okay. So then, maybe we can see this a little bit better. All right, see that? That is, that's called a reflectance array. And what it is it's 6 infrared receivers. And it's analog, basically saying how bright is the surface that I'm looking at right now. And if this weren't so blurry, you'd see that each one of these is actually 2 components. One of them is an emitter, so that's just a LED that emits light, so it can bounce off the surface and come back. And it's infrared, so you don't see it. But each one of these sends light down and then receives it back and tells you, really, are you looking at something dark or are you looking at something light? It then connects off to the Arduino. There's the analog pins there. And if we move over here, you'll see that there's this gray and white. That's the emitter. That's the pin that says turn the light on and power this sensor. And what this allows you to do is you can detect a line. We can start talking about a self-driving car now based off of a line. And that's what we're looking at here. And in a lot of systems, if you had something like this, you'd have 6 sensors, and you'd have to figure out where's the line. But the nice thing about the API and something like Johnny 5 is, yeah, you can just get the raw data events as they come in, but you can also get a line event. And the line event gives you a number. In this case, because there are 6 of them, it's between 0 and 5,000. Where is the line under my sensor array? And so all the way on the left is 0, all the way on the right is 5,000. If you're in the center, it's 2,500. And it's able to figure that out by doing just some basic averaging and weighting of these different values. And that's all internal. It doesn't really matter that much. You've got this interface that just says, I'll tell you where the line is. You figure out the rest. And so if your car's driving along and you hit a threshold, let's say 1,000 is your threshold. So it's gone past this space right here. 900 is your value. Which way do you have to turn the car to bring it back on? Left, that's right. So if the line is to the left, you have to move left. Similar, if the line is to the right, you have to move right. So this is the entire app to drive the car. I have my car, of course, so that's been abstracted away. But it's, it was pretty simple. And now I've got a reflectance array. I tell it where the emitter is. It's on pin 13. And then I've got my analog pins for those 6 sensors. And then I have it auto-calibrate is true. These things have to be calibrated. You can either load a calibration file or there's an API for doing all sorts of calibrations. This particular one, just to make it nice and easy, I'm going to tell it to auto-calibrate, which means I'm going to hold it for a moment and just bring all the sensors over white and black just so it can see what it's trying to do. And so we say enable the device and then listen to the line event. If it's less than 1,000, turn left. If it's greater than 4,000, turn right. Else, go forward. Again, I'm going to do the quick calibration. Okay, ready? Go. This is a race we did at CodeMesh where we gave you this code basically and said, you need to innovate on this design to make it faster. And this default software hardware configuration finishes in approximately 45 seconds. But the winner did it in under 20, if I remember correctly. And this is where it gets to be fun. This is where you can forget about electronics a little bit and start getting creative in 3 different dimensions. Because there are really 3 different ways in which you can make this thing better. There's the software. Like that algorithm that we have, it works. Anybody have ideas on how you might make this a little bit faster?
Tighten the parameter constraints?
Yep, there's tighten the parameter constraints. Yep. Give you a hint. Left is pivot. It's not moving forward when it's turning. So what could you do to make it be a little more optimized?
Drive left.
Drive left. That's right. And maybe you could even optimize it. You drive hard left, or you'll give it a parameter, between 0 and 1 or whatever, and say, where 0 is pivot, but and 1 is straight, but 0.5 goes like that. So depending on how far off you are, you can adjust accordingly. And then what happens is it actually, you get your algorithm tight enough, and this thing isn't doing this choppy thing. It's actually just following the line, and so you save some time there. So that's the software. There's other things you can do, things like proportional integral differential PID algorithms. These are the types of things that are used in balance bots and sous vide machines and all sorts of things that basically say, I've got a set point I want to get to, and knowing things about historical data and making assumptions about future data, it uses integrals and differentials to do it. But the cool thing is there's a node module for that. You just bring down the PID node module, and then you can do the same thing. And so what you do is you say, I want this thing to always be at 2500, and it figures out using a dampened frequency, harmonic, whatever, blah, 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 theory. It just kind of figures it out for you, and then you can actually get it to a point where it's really smart and smooth. So that's software. But there's also, that's the first of the 3 dimensions. The next one is electronics. It turns out there are things you can do with the electronics to make this thing faster. You can overdrive these servos. There's only 5 volts coming out of the board. These are 6-volt servos. This is a 9-volt battery. I can directly drive this 6-volt servo with a 9-volt battery. You might get some smoke. It's a risk you're going to take because you're racing. It's like hacking your engine. You may blow out. You may blow a piston. I don't know. I don't even know anything about engines. But you may blow your engine out, but that's the risk you're going to take to be faster. You can do that, and you can get this thing to be faster. Then that's the second dimension. The third dimension is the physical side. Anybody got any ideas what you could do physically to this thing to make it faster?
Make the wheels bigger?
It's the easiest hack, yeah. You make the wheels bigger. You make the wheels this big, the thing flies. Your algorithm has to be tighter. So there are all sorts of things you can do to be creative, and at CodeMash, has anybody ever been to CodeMash? It's a really cool conference in Ohio that happens every January. About 2,500 people go, and we did an event there where it was an all-day event, 2 days, 100 people each day, and so you can imagine just 100 people building these things. The place was trashed because we just gave them a whole bunch of material because this platform, this is just wood, and wood slips on this. And you have to do something to make it have some friction. This is shelf liner. That's all this is with some hot glue. It's one way to do it. But we gave people like rubber gloves and PVC pipe and all these things. People created all sorts of crazy wheels and things like that. And it was really just a flutter of activity. It was a ton of fun, and it makes people who are normally software developers and know how to solve problems have to think in different dimensions. And honestly, people didn't spend a lot of time on the software. They spent time on the things that were a little more fun to them. They're like, okay, I can figure out the algorithm. How do I make this thing go faster? All right. So we'll put this platform away for a little bit. It'll come back. Next one's cool. I like this one. This robot is called the OMNIBOT. It's affectionately named Alf in the office. Don't even know why they called it Alf. And this thing has 3 wheels on it. How in the world is this thing going to drive, right? Well, it turns out there are these wheels that have wheels on them. So now we're talking about vector mathematics. What this thing can do that thing can't is it can go in any direction at any time. That thing there has to turn, pivot, and go forward. This thing can strafe. This thing, you can write an algorithm to have this thing go around like this. So you can imagine you have one of these bots and maybe you put a laser on it and you start playing laser tag and treat it like Doom and do these crazy strafe maneuvers. It can rotate. It's way more agile than the other board. Now, in this case, we're using motors. We're not using servos. So we're just, we'll talk about the mathematics in a moment. This is what is called a shield for Arduino. It's really just a thing that snaps right on top of the Arduino. It's got all those pins, just piggybacks on top of it. And it's the motor controllers for the motors. The thing is, motors, when they come to you, they have brushes and they turn, and you apply a current to it, a voltage and a current, and they turn. And if you reverse that current, they turn the opposite direction. But how do you control that from a pin that's digital? It's hard. And then the board itself doesn't put out a lot of current, and so you need to amplify the signals that you send. And so you need a couple of things. You need an amplifier circuit, which is really just some transistors and capacitors and resistors. And then you need something called an H-bridge. And I'm not going to get into too many details on what an H-bridge is, other than the fact that it's something that allows you to switch the direction of the current, which allows you to change the direction of the motor. All this stuff is something that is inside those servos. But this gives you more control now. You can add giant motors to this, and you can really, you can up the wattage. There's all sorts of cool things you can do once you say I've got a motor and a motor controller. Now, and this board itself can control 4 motors at the same time. The 4 motors need these H-bridges, and the H-bridges each take about 3 or 4 pins themselves. Now the Arduino doesn't have that many pins, digital pins at least. And so the things on the outside, the black lines on the outside, those are the H bridges, the amplifier / current switching. The thing in the center is called a shift register. And all a shift register is, it's like a little piece, it's like a 16 bits of memory. And the way it works is it's got a latch bit, and it has a value to go up and down. And so you can just say on, shift, off, shift, on, shift, off, shift. And these bits get pushed onto the shift register. And then they go out the chip, which now means I can get 16 pins with only 3 pins of control, basically. I have a enable bit, I have a data bit, and I have a clock bit, basically, that will set this thing through. And so if I want, so I have to now do a whole bunch of math to figure out what the values are going to be of all the different bits in order to get all these motors to go on, and which direction, and how fast, and all that stuff. But the cool thing about Johnny 5 is that Johnny 5 knows about this thing. It's called the Adafruit version 1 shield. And so I can just say it's a motor with on motor 1, 2, and 3. And it just kind of takes care of it for you. It allows us now to forget about hardware, from the software's perspective at least, and think about vector mathematics. If you want to get from A to B, so you have an angle and a magnitude, and we have these fixed vectors, essentially. You can get there by making sure that wheel 2 goes a lot harder than wheel 1, which goes a lot harder than wheel 3, and you can get to where you want to be. And that's really all that's the rest of this code is. You know, my OMNIBOT has an API that says I want to move to a particular angle and magnitude, and then it goes and breaks it up into an XY vector, which breaks it off into then 3 different vectors for the motor. And it's not actually that complicated of math. I did not come up with this math. I'm not clever enough to come up with this math. I got it off of Make magazine. I translated C code to JavaScript. And now it works over here. So let's look at a demo of this running. I have this thing running. This thing draws a lot more current than the servos do, so I just have 2 batteries in parallel here, just to help it along a little bit. And I'm really bad at controlling this thing, by the way. So bear with me, because it moves too fast, and I just never got the demo to go slower. So yeah, let's drive the OMNIBOT. Right, kind of cool. You can start to imagine some really cool things you can do with it. One thing that we started building is something with a whole bunch of light sensors all the way around it. And it was called the tractor bot. And you'd have everybody would get laser pointers, and they would try to hit the light sensor, which would cause it to go in the direction of the sensor that was being hit. And you try to basically, it's like a tractor beam, right? And you're just kind of pulling it in with your light, and whoever would get it out of the circle in their quadrant would win. Like I said, you can turn this into laser tag. You can just drive it around and annoy the cats, whatever. There's what you do with it is your own imagination. I forgot to show then. So once I've got that abstracted out into an OMNIBOT, I do a very similar thing. Instead of mapping keys directly to a command, I'm just doing to an angle magnitude pair. And then I just say, all right, if the key has been mapped, then go to the angle magnitude, and it works. So there are lots and lots of components supported by this library out of the box. You've seen the servo, and you've seen the motor. those two things on the upper left. There's the light sensor, a flame sensor, which can tell you whether or not things are on fire. Joystick. This thing here is an accelerometer, gyroscope, temperature sensor all in one. This is a temperature sensor. This is a PIEZO buzzer. A relay to like switch on AC circuits. You control your lights with this thing. Proximity sensor. This thing here is a ping sensor. It sends out a tick and listens to how long it takes, and so it can tell how far away things are. It's a different way of detecting distance, and kind of like the reflectance sensor in some ways. All sorts of different LED components. You have regular LEDs, you have RGB LEDs, you have 8x8 LED arrays, you have 8-segment LEDs, all those things are all supported. Switches, this isn't all of them, this is just a bunch of them. And every single one of them has this, this very intuitive shape that goes along with it. So let's take a look at this real quick. What I have here, this is a different type of shield. It's just a shield that gives me some space to put a breadboard right on it. That's all. I just glued it to it. It includes a couple extra switches built in and an LED and things like that, but it's easy to breadboard. So I just have this thing connected up. In this case, it's the pin 11, but this is a diagram to show pin 13. Really, really straightforward. And the API looks like that. And so now, let's see, can you see this over here? Yeah, so let's bring up the LED code. Oh, I want to show one more thing. This code in the bottom here that says REPL inject. Johnny 5 just brings up the Node.js REPL loop that allows you to write code right in it, and then it'll inject your object into it. So now the LED is available to me from the command prompt. So this code I'll run over here as the LED example. Move this over so you can see the LED going. And so then the API is very simple, led.on, right? And led.off. Pretty much what you'd expect. You can control brightness. So it's between 0 and 255. We'll just do 100, and let's go down to 10. Now you've got brightness control. I'll talk a little bit about how that works in a moment. Strobe and pulse. So let's look at strobe. Just blinks. It's just a blinker. You can give it a number in there, and that's how much time in between state changes. That's 1 second, 1,000 milliseconds. You can also pulse. And pulse just animates the brightness now. So instead of on, off, it animates over time between 0 and 255, back and forth. And then if I want to stop these movements, I just say off. And did I do that right? Sorry, stop. Off is turn it off. Stop is stopping the animation, right there. But then off is something I have to call too because it stops it where it is, and so off just turns it off. All right, cool. We can talk a little bit about how it does brightness because this is also how the servos are controlled. It uses something called pulse width modulation. And with digital pins, and I should add that Arduinos do not have analog out. The reason they don't have analog out is because digital to analog converters are hard and expensive. This is why you can buy separate digital analog converters for your headphones to do it better than the things that are built into your computers themselves. And so it's too expensive to put in an Arduino. You can do analog in, that's a lot easier, but analog out is just a harder circuit to write and get right. But you can, in some cases, you can approximate it using a digital pin, using this concept of pulse width modulation. And what you're really doing is saying, for a percentage of the time, called the duty cycle, it's going to be on. So if I want it to be 10% brightness, essentially, I'm really sending a pulse with a 10% duty cycle. If I want it to be 50% brightness, I would do 50% duty cycle. If I want 90% brightness, 90% duty cycle. If I want it on, it's just on. And so the servos are controlled that way too. Servos respond to pulse width modulation. That's all handled for you internally. The Arduino itself has several pins that do pulse width modulation automatically. And so Johnny 5 knows, well, if I'm on this pin, I'm going to just tell the board to go at this value. But if I'm not, well, I'll use the clock and I'll do my own pulsing. So you can use servos on other pins. It's the same way then that this RGB sensor works. It's right here. The RGB sensor there it is really just 3 LEDs. It's like a pixel on your monitor. It's just much brighter. And so it has 3 different pins that control the 3 different colors. And then depending on the type, you either ground it or power it. And that would be anode or cathode-based LED. And so in this code, it's an anode-based. So I say is anode is true, and I say pins are 9, 10, and 11. And then I get a very similar API, but different because it's an RGB. That becomes available to me. And maybe I can get this to work with the camera, maybe. Let's see. There you go. Thank you. Thank you. That helps. So yeah, RGB, we're going to run this thing. And so I can turn it off to begin with. And then I can say color. And the thing is, all these APIs, they try to make them as accessible to programmers that, we don't have to think too much about, hardware. We know hash-based RGB colors, right? So hash FF0000, there's red, right? And then I can come in and green and blue. I want purple. Well, I'll mix my reds and doesn't come through on the camera that well, but it's purple. My red and my blue, but this could be at any level. And so I could do, not so much blue. I could just, let's go to 55. It's a slightly different shade. And so, you can imagine status indicators with these things using the color. And then it has the same, okay, that's good, thank you. It has the same API as the LED does, the off, the strobe, the stop, all that stuff, same thing. PIEZO buzzers. So PIEZO buzzer is really, it's kind of like a little tiny speaker. You send it a voltage and it makes a little tick. You pull it off and it makes a little tick. It's crude. It's not high fidelity. Doesn't really matter because we're just playing. We can send pulses to it now. And so any musicians out here? Music theory? In the Western scale, the note A is 440 or 220 or 880. It doubles every single time. Every octave just doubles. And so 440 is the note A. And so I can play the note A if I want now, the hertz of just 440 for a half a second. Let's do that. I'm going to uncomment this because it's just a little bit easier in this case. Right. Now, that's not that interesting. You can do a buzzer, sure, that's cool. You want to do a doorbell, that's fine. But there's a whole API here for playing a song. These are the notes, the rests, the beats, the tempo. And now I can play a song. See if anybody can recognize the song. Nobody? You've just been rickrolled. Right? If one person got it. Yeah, but then there's also there's an NPM module out there called J5 Songs, which has a whole bunch of prepackaged songs for you. So I'm sure most of you at least will recognize this song. Right? We can have a little more fun with it. And I don't know who did this one. They didn't quite get it right, but it's close enough. I don't need to listen to it all. There's all sorts of, like, if I remember correctly, klaxon is one that's there. Just, it's like a klaxon. That's all it is. Let's see. Pew, pew, pew. I think that's right. Hopefully that's right. Right. There's a whole bunch of them out there. So if you want to do a doorbell, there's a couple of doorbell sounds as well. And if you wanted something else, you would just have to go find the music sheet for it and write it, and it would be there. So that's kind of fun. The wiring for the PIEZO is really straightforward. Ground it and give it a signal pin. And then in the code, you just tell it what pin it is, and it just works. Kind of magical. Okay, so let's get away from the Arduino. Everything's been on Arduino because it's convenient, but I'm selling this thing as being a really cool framework that abstracts all the things. And so we're going to move now to the IMP. Now the IMP, like I said, this is just an SD card that has a microprocessor and a Wi-Fi chip on it. And we'll look at the code again. Instead of having this Fermata layer that talks serial, you replace the Fermata software in JavaScript with something called the imp.io, which goes to the cloud, to the electronicimp.com/agent ID. Every device just gets a hash, essentially, which is an agent ID, which then comes back down from the cloud to talk to a firmware that's running on this thing called Tyrion. And I didn't make the names, but it's funny. Anyways, it goes two ways. It's bidirectional. And so you can start to think about the things you can do with this to make it cloud-enabled. Your code doesn't need to be necessarily running in the same place. All sorts of cool things you can do with it. But everything else ends up being the same. You just, you got your pinouts, you connect it up, and sorry. The only thing you do to say that it's using an IMP and not an Arduino is you bring in the IMP I/O layer. It's just an NPM module, npm install imp.io, require it, and then when you bring up the board, before you just say new board, now I say, well, here's my I/O layer. I'm going to create an IMP I/O layer with my agent ID. And how do I get an agent ID? This is just brilliant. There's a phone app. it needs to connect to the Wi-Fi. How do I connect an SD card to the Wi-Fi? Well, I'm connected to Atomic Object Guest. I plug this thing in. I say, OK, send up, link up. I go like that. And it tells it all the Wi-Fi information it needs. Kid you not? This is how it works. It then connects up to the web, registers itself, comes back down and tells you what the agent ID is. I did this before I started, so we don't have to wait for it. But it's hard to see, but there's a little infrared, a light sensor right there. And it just does it, which is cool. So like, again, let's say you wanted to do a device that was Wi-Fi enabled. You build your circuit with an SD card, you slap this thing in, and you can take this blink up thing that you just saw and embed it in your own phone app. And then you can program your device with your app, and the user doesn't need to think too much about it. It's just like, okay, get the phone app, turn the device on, pick the network, and put it on your device. And then all of a sudden it's on the web, and then everything else communicates. It creates a REST API for you. You actually have the capability of creating all sorts of configurable REST APIs, but that's kind of what the Tyrian firmware does for you. So just to kind of show, this is just kind of plugged into power. You can do this with battery as well, but power is just easier for demos. I'm just doing a motion sensor. Real simple to just kind of show that this all works. This here is a proximity sensor, which will basically send a signal up when somebody's nearby. You use these in security systems. And then I've got an LED connected. I'm going to have this pointing away from the crowd, so I can, a little bit have a little more control over it. Yeah. But you look at the code, so everything. The only real difference is you bring in the I/O layer, and then everything else is the same. I just create my configuration for my LED and my motion sensor, and then I say when motion starts, turn the LED on, and when motion ends, turn it off. Really straightforward. Assuming everything is connected to the cloud properly, we're going to run the code. We're connected, and so now, there.
Can you turn the head around?
The what?
It's behind the projector.
Oh, I'm sorry. Yeah. So the light's on. I can only go so far with this thing. The light's on. It'll turn off. This device here, because it's used for security systems, we'll keep it on for a while. So we'll probably turn off in a moment here. It just hasn't sent us the motion off yet because the device doesn't do it. I think I'm moving. Let's see. Yeah, see. There you go. Now I move and it turns back on. So cloud-enabled, JavaScript-powered machine. And again, there are a dozen different boards that it supports. That's just one example. I just think that one's cool. So I showed it. Okay. Kids can play too. This is particularly favorite of mine because I'm a part of this project. And I'm doing it because my daughter is really interested in all this stuff. Loves Scratch. Has anybody played with Scratch at all? She loves Scratch. Very uninterested in code. And so Robotnik is a platform for doing that. And so let me run the server. It's also an open source. This is all in Git. Everything, the Robotnik, this presentation, Johnny 5, it's all Git-based. So I'm going to run the server. Okay, we're at 8057. So there we go. We're going to use the line follower bot. And so this is all like, this is demoware. We're working on it. But what I'm showing you is really working. So I can say when the red button is pressed. And what do I mean by that? When I execute, I get a little panel with a joystick and 2 buttons here. So when the red button is pressed, I want to do something. We'll just say, for now, turn the LED on, and when it's not, turn the LED off. And the cool thing about this is it is a bridge to code, because it generates JavaScript code that you can copy into a buffer and you can modify yourself. If you want to do something more complicated, you can. This is the code. It takes this code and it sends it down to the board. But if I execute it now, that's just booting up. And now I come over here and hit the red button, right? I've got my logic. But we can, of course, extend this and say when the up button is pressed, we're going to say that the left motor goes counterclockwise and the right motor goes clockwise. Sorry, the right one. And when it's done, the left motor is going to stop and the right motor will do the same. You can send that code. Again, there's our code. Can send that code up to over to the board, or it's actually sending it from the browser to the node server, which runs it through Vermata in this case. But and so now if I use the joystick and go forward, I can control my bot. And so this gives kids ability to maybe learn JavaScript in the process, but play with hardware in a very accessible way. Very excited about this project. I can't wait to see where it goes. We're hoping to have something really usable and packaged, so you don't have to like git, clone, repo, npm install, install node 2, and all that stuff. It's going to be like packaged as a Chromium app. So you just download and run. That's being done by somebody else on the team. So by summertime, because it turns out there's something called the International NodeBots Day. It's on July 25th, and places all over the world are going to have NodeBot building events. Ann Arbor is going to be one of those places, along with like Sydney and Paris and other much more amazing places. I like Ann Arbor, but it's not Sydney or Paris. And so we're hoping to have this as something that all of the places can use and invite your kids and things like that. So I think it's cool. And this is kind of the example of what I was talking about, where it's like, I'm not doing JavaScript robotics because I only do JavaScript. I do lots of other languages. I'm doing JavaScript robotics because it enables things like this very easily. This isn't a lot of code. There's way more UI front-end code here than there is back-end code. The ecosystem that is Node.js and Johnny 5 and everything that's happening in that space right now is just such a flurry that we're doing really cool things with the things that come out of it. So I'm excited about it. It's really just the tip of the iceberg. Your creativity is the biggest limiting factor here. My creativity is the biggest limiting factor. This isn't that creative. It's a car. I've seen some really, really cool things where it's like, man, this is where I talk about the people with amazing ideas are enabled with this accessible language. It may not be the most perfect language in the world. I'm not saying that. I'm just saying that it's accessible and it's easy and the ecosystem supports us in a way that's really, really cool. And so I hope I've made the case that using JavaScript for robotics is a good idea. It's not a dumb idea. Play with it. Arduinos cost 15 bucks. Node is free. Johnny 5 is free. All this stuff is free other than stuff you see here. This entire kit, $30. Cut some wood out. This is a hole saw, just with a drill. Attach it to some servos. 9-volt battery. You don't even need some of this stuff. You don't need, this sensor is $10. You don't need the sensor to play. Caster wheel. I'm sure you can come up with something cheaper than that. Or this is only $1, but you probably come up with something cheaper than that. Put it on some straws, so it's just like, and put it on carpet, so it's like going around. Put staples in and like studded tires and put it on your carpet with some plastic down here so it can slide around and have it be a carpet bot. I don't know. Anyways, I don't have this one link on here because I forgot to add it. There's a website for Johnny 5 that has examples for everything. It has the entire platform support that we were talking about, all the boards that it supports. The API is all here and documented. And then this is really cool, are the examples. There are schematics that go with all the component examples. So this is where it also makes it really accessible. This is the community thing that happens. The community got together and really documented this really well and said, I want to enable somebody that doesn't know much about electronics to do things with electronics. And we can't just say, go hook up an LED. What does that mean? That's what it means. It looks just like that. Go do it and run this code, and it's going to blink. Servo, same idea. Here's just some information on how to use it. That's how you hook it up. The motor, same thing. Just this is the most simple way to do the motor. You don't get all the control we were talking about. It's not going to go that fast, but it's a simple way to do it. There's just all sorts of things in here. Here we go. It's electronic speed controller. Anybody done RC airplanes and cars and such with electronic speed controllers? These things are essentially circuits that drive high-powered, like brushless motors and such. Like this is an example of a 30-amp speed controller. And this gives you really fine-grained control over your motor. Let's say you've got an RC airplane. You want really good control over that propeller speed. And you want to be able to ramp it up quickly and draw a lot of current really quickly. That's what the speed controller does. You buy them from hobby stores. But there's a Johnny 5 component that you can hook up to it, and an API to control it, and a schematic to show you how to use it. And so, if you first heard that, oh, you can hook up a speed controller to your Arduino, and you don't know much about electronics, you'd say, okay, I believe you. But now you can hook this up and give it a try, and it works. So, anyways, it's Johnny 5 IO. And then these lightning talks, this talk is online. This started out as a lightning talk, and so the Git repo says lightning talk, but it is what it is. The Johnny 5 Git repo itself is just, it's here, but it's better probably to go to the Johnny 5 website itself and just click on the GitHub link. What else is here? The chat room for Johnny 5 is just hopping. I mean, this is all just in the last hour or so. This is the community talking about how to make things happen. And then Johnny 5 is just one way to do the concept of nodebots. Nodebots is a bigger umbrella of JavaScript-powered robots. Johnny 5 is not the only framework for doing this stuff. There are also Internet of Things frameworks, which is different than hardware. And the Internet of Things is more about how do these things communicate through the internet. The hardware layer is still kind of unknown with these frameworks. And so Johnny 5 kind of gets in there and says, well, this is how you talk to the hardware. Now plug this into an Internet of Things framework and have all these things connect across the globe or across offices or however you want to do it.